1, fire!
On January 24, 1991, the Institute of Space and Astronomical Science of Japan launched lunar probe named Shijun, which goal was to verify technologies and techniques required for future planetary or lunar missions. It was supposed to fly close to the moon before launching the second probe, Kagoromo, which objective was to orbit the moon and transmit data back to the Earth. Launch succeeded, but there was a problem. Kagoromo was silent. Japanese could see it, but the transmitter didn't work, so there was no way of knowing if it successfully inserted itself into lunar orbit or if it was on the trajectory around the Sun. This was a catastrophe which meant mission failure. There was only one way to save the day. The first probe, Hiten, would have to enter lunar's orbit. However, there was a problem. Hiten was not designed for that. Not only that its engines were not strong enough, it also didn't have enough fuel. Luckily, there was a mathematician in America named Edward Bruno, who was just fired from NASA for experimenting with chaos theory in celestial mechanics. He later said the Japanese contacted him and said, "We think your work is BS, but we will try anything." In this video, we will see how the chaos theory is in the heart of celestial mechanics and how understanding that revolutionized space travel. On July 5, 1687, Sir Isaac Newton published arguably the most important book in the history of science, Philosophiae Naturalis Principia Mathematica, which Lagrange characterized as the greatest production of the human mind. The book forms the foundation of classical mechanics and gravity. He states 3 laws of motion which correctly and fully describe dynamics of any objects. These laws are: a body remains at rest or in a motion at a constant speed in a straight line unless acted upon by a force. When a body is acted upon by a force, the body's acceleration multiplied by its mass is equal to the force. And if 2 bodies exert forces on each other, these forces have the same magnitude but the opposite directions. This law implies that if we have an object and we know its initial position and velocity and all the forces acting on it at any moment, we can determine its motion for any time in the future or in the past. For us, even more important is his law of gravity, which states that every particle attracts every other particle in the universe with a force that is proportional to the product of their masses and inversely proportional to the square of their distance between their centers. In other words, closer and heavier the objects are, the stronger is gravitational force between them. Equipped with these laws and with his another invention, calculus, Newton was able to solve so-called two-body problem. Predict the motion of 2 massive objects if we know their initial positions and velocities. He proved that if we have 2 objects and one of them is significantly heavier than the other one, their motion can follow one of the 3 orbits, the conic sections, ellipse, parabola or hyperbola. The natural question one can ask himself after solving 2-body problem is, can we describe a motion of 3 bodies? This turned out to be a difficult question, which became very important in 1714 when British Parliament offered £20,000 or $3 million in today's money for a method to determine the longitude at sea to an accuracy of half a degree. In the absence of accurate clocks that could function at sea, a lunar table along with the observed position of the moon was the principal method of estimating the longitude. Understanding and predicting the motion of the sun, the earth and the moon gained an enormous importance, capturing the attention of some of the greatest mathematicians of that time. But this problem turned out to be significantly more difficult than the simple 2-body problem, and it was soon observed that under most starting positions, orbits were impossible to determine analytically. Now we are entering in the realm of chaos. So what is that and how it is connected to the 3-body problem? We will first explain chaos on an example of double pendulum. This simulation shows that the motion is indeed chaotic, but this is not what mathematical chaos theory is about. In mathematics, an object behaves chaotic if it gives us very different results under slightly different initial conditions. For example, suppose we have 2 double pendulums with almost the same initial position and velocity. At first, it looked like that we only have one pendulum, as both started from almost the same position, but after some time, we can see that their motion is completely different. We know that such system is determined by its initial position and velocity, but in practical applications, it is impossible to determine how it will behave after some time, because in real life we can never know initial conditions accurately on infinite decimal places, and even a small error can in time cause big differences. A real-life example of this is weather forecast. Even though weather is completely deterministic, it is still almost impossible to calculate it with a precision for a week in advance. Alright, now that we have some idea what is chaos, we're gonna look at how it appears in free-body problem. Suppose there are three massive bodies acting one on another with gravitational force. Their motion looks extremely random, and this simulation will show us that it is indeed chaotic. The initial positions of objects in free-body problems were respectively the same, and their initial velocities differ very slightly. However, we can see that their orbits are completely different. The first one who figured that out was the great mathematician Hsing Lo in 1890. He said, "Small differences in where the three bodies start may produce very great differences in where they finish, so that prediction becomes impossible." This observation marked the beginning of modern chaos theory. Okay, now it's time to go back to our story. Where were we? Yes, Japanese contacted Bel Bruno in hope that he will save their mission by helping them get their spacecraft hidden in the lunar's orbit. He had to consider four-body problem consisting of the Sun, the Earth, the Moon, and Shijun. Aware of the chaotic nature of four-body problem, he knew that if he changes the velocity of Shijun very little, he will not use a lot of fuel, and the spacecraft can reach many different orbits. Fun fact is that Bel Bruno is not only a mathematician but also a painter, so he painted his thought process. This is his artwork. His plan was that the Shijun would go into the direction of the Sun, which was at the time very counterintuitive. For example, the Apollo 11 mission used almost the opposite route, but the Sun's gravity is almost 2 times stronger than the one of the Moon, so he knew that for that path, Shijun wouldn't need a lot of fuel. He was looking for the trajectory that went into the direction of the Sun, but would after some time come back to the Earth in the vicinity of the Moon, which would then pull the spacecraft into its orbit. After some testing, Japanese went with Bel Bruno's plan, and in October 1991, the spacecraft Shijun successfully entered lunar orbit. This was a remarkable success, making Japan only the third country with that achievement after the Soviet Union and the USA. Bel Bruno went in history books as the man who revolutionized space travel. His method, called low-energy transfer, is today used all the time, as it enables us fuel-efficient, low-cost space travel. He succeeded because he understood at first glance two very different concepts: the theory of chaos and space traveling.